This week we'll be looking at addressing some of the shortcomings that we've had so far with our forward kinematics. It's probably not something you've measured thus far, but what you might find if you were to run your robot through a bunch of different position control tasks, you'd find that it was off the mark more often than not. And that's due to some errors in the system. So I've added a widget to this chapter's page, and what this lets you do is explore a little bit about the different impacts of different types of accumulated error. So describing this widget a little bit, the robot starts at 0, 0, and there are actually two lines being drawn, one in black and one in blue, and you'll see both of them when they start to diverge from one another when I add some noise to the system. The robot starts at the origin and is supposed to come to a target down here at 1, negative 1. After it hits that target, its target updates, or its goal updates, to this one here at 1, 1. So it'll sweep down and then turn hard left as it can, given the different parameters for the control system, up here to the final target. And currently, we've been assuming that our robot follows the exact path it thinks it follows. But forward kinematics doesn't take into account errors that can build up. In fact, if you were to take the wheels off of your robot and run the forward kinematics or the position control process, it'll happily drive itself to some location without moving anywhere. And the error would be whatever the distance is from the origin to that final location. And that's because the forward kinematics operate using only the wheel encoders as the source of information. And the wheel encoders don't have any knowledge of how the robot's actually moving around in space. They only know how the axle of the motor is turning. So if the wheel slips, the wheel encoders won't register that. If the robot hits a little rough patch in the carpet, maybe the carpet's torn in some spot and gets bumped off course, the wheel encoders don't register that either. And so that builds up in the form of noise. And so I haven't modeled noise perfectly in the simulation. In fact, there are multiple sources of noise, just from the censoring side on the wheel encoders to the actual slipping of the motors themselves, or the inaccuracies of the motors themselves. Instead, I just sort of packaged those all together and said that the left motor will have some noise to it from both the sensing and actuation side, and so will the right. If we add just a little bit of noise magnitude that's still sort of centered on 0, the robot more or less follows the path it thinks it's following. So again, the black line is the true path, the blue line is the true path, where the robot actually ends up, and the black line is where it thinks it is. And if I restart this multiple times, you can see for the most part, it's tracking to its goal, or close enough that you might not actually notice. If I increase the noise, for the most part, it's still following that same path, but it ends up in a larger range of possible final locations. I could increase it even more, and again, you see the same sort of effect. For the most part, it's still on track. Where things go really wrong is if there's some sort of bias to the system. So let me crank the noise down, and let's say that the left motor is not just noisy, but the left motor is almost always going a little bit faster than it registers as going. In that case, this thing's almost always turning off to the right a little bit more, which is why you see it ends up to the right of the target here, and even more to the right of the target here. And no matter how many times I run this, it's likely to have that problem. If this were to be balanced and both motors registered off a little bit, then again we kind of get back to that same problem. But if I crank them both up, you'll find that it just travels a lot further than it thinks it is, because the bias is equal and balanced, but it's just basically saying it's moved much further than it thinks it's moved. So I'll encourage you to play around with these different values and see what happens to the simulation as different types of noise enter the system. All right, well, one way to combat this would be to have a camera mounted somewhere in a fixed location in the room that tracks the robot and tells the robot exactly where it is. That's not always going to be handy, and so there are things we can do to our robot itself that can improve its localization or pose estimation. You'll hear me start to use both of those terms interchangeably. Normally I'll use pose estimation when I'm not worrying about noise, and I'll start to use the term localization when noise becomes a bigger and bigger factor, and we need to fuse multiple sources of information for providing an estimate of where we are in space. Well, the first thing we're going to do to improve this, and one example I can give you is if I give ourselves a little bit of bias on one side and no bias on the other side, you can see with a little bit of bias, the robot's just always turning a little bit more left than it thinks it should be turning. Well, one way to correct this discrepancy between where it actually is and where it thinks it is to provide it some more information on its actual heading. So the next sensor we're adding to our robot is this magnetometer, also known as a digital compass or a magnetic compass, and this is a triple axis magnetic compass. Zooming in on the actual breakout board here, this is the small little chip here that is the actual magnetic compass. And you can see it gives you the reference here. It's saying it considers the x-axis in this direction, the y-axis in this direction, and the z-axis coming straight out of the board. This is a breakout board in that it takes the magnetic chip, the magnetic compass chip, adds all of the extra little resistors and capacitors that are needed to make it function properly, and then makes it easy to attach to the pins. If it wasn't on this breakout board, we would have to solder directly to the little pads here on the magnetic compass chip itself. All in all though, all this does is make it easier to use this chip. We would still want to look at the datasheet to see how this chip functions. And I'll give you a few of the highlights of the datasheet. I'm not going to ask you to read through the entire thing because we're not going to be treating this class like an embedded systems class where we're learning how to write device drivers. Instead, we'll mostly just get a rough estimate of how we can use the chip, or if we can use this chip, and then we'll rely on some kind soul out there that's already written a library for the chip itself. Alright, so what are the highlights of this chip? Well, its operating voltage is in the 2.16 to 3.6 volt range, and that works well with our microcontroller. Our ESP32S3 considers 3.6 volts high. And there are other microcontrollers that would consider 5 volts high, and those other microcontrollers would have a little bit more difficulty interacting with this chip than we will. They'd have to use something called a level shifter in between to change the high voltages from one to the other. So that's the first thing I would point out here. The next to look at is the specifications table here. It says the range for the supply voltage, the range of the input-output voltages. So those are slightly different. Supply is what we're plugging in as sort of the power and ground, and I/O is gives you a range on what it considers possible for registering a value as a logical high, meaning 1, and a logical low, meaning 0. The rest of this gives some information on temperature and hysteresis. Most of that we can just safely skip for now. If we were really concerned about operating duration of our robots, we'd also want to look at the current draw. But again, we'll just skip through most of that for now. And I'll bring you down to this absolute ratings table and the I/O characteristics table. So this does tell us that this chip can operate up to 5.4 volts, but that's going to have some extra that's going to come with some extra work. And in fact, we'd want to take a look at the temperature of the device, because as it gets hotter, the characteristics of the chip are going to change. So we're likely not going to want to get anywhere near this 5.4 volts. Another table that's useful to look at is this table that gives us the I/O characteristics, the input-output characteristics. So what does it consider an input high, an input low, an output high, and an output low? Well, from our microcontroller, if our microcontroller gives it anything within a range 70% of VDD and VDD plus 0.3, it's going to consider that a high voltage, or otherwise known as a logical 1. So what do they mean by 0.7 times VDD? Well, if VDD is 3.6 volts, it means we can go down to as far as 0.7 times 3.6. Which means we can go all the way down to 2.5 volts, and it'll still consider that a high input voltage. Likewise, we can, on the other side, have a 0 register as high as 20% of VDD. So if your output from your microcontroller is 0.7, the compass is going to consider that a 0. So that's what this table is giving us, just some information on what valid ranges are. The rest of the data sheet isn't going to be all that interesting to us. It's going to talk about the package, but like I said, we're using this breakout board version, and they did all the work of making the package work with all the peripherals and giving us some nice pins to solder to. The next thing to look at is about the basic device operation. Most of this we've already covered. The range for VDD. It'll talk about some input timing. So for example, how long do you need to leave a value high before it gets registered by the magnetic compass? Same for on the low side. And you may not ever think about it this way, but it actually takes time for you to ramp up from 0 volts up to the high voltage range. And so that's what this little diagram here is showing us. The more important part is the fact that this is going to use the I2C interface to communicate. And it also tells us its address. So in code, we'll need to use this 0001101 address when we're trying to speak to this device. You may remember that our OLED display is also on the I2C bus. And so as long as we have the correct addresses, we'll be able to address both our magnetic compass and the OLED on the exact same address bus. Which means in total we have to use fewer pins on our microcontroller. We only have to use 2 digital pins so that we can communicate with 2 separate devices. That's a pretty big win, especially as we add additional communication, additional peripherals to our robot. Alright, well that's the end of what I wanted to show here in the datasheet and introducing the problem. So in the next video, we'll discuss a little bit about how to get started with the Arduino library for this device.